Yeah, now we'll see another example. So in this case, a 4-bar link mechanism with the following dimensions is acted upon by a force 80 newtons, 150 degree. This is the given data. So the force F acts at point E on this link DC. So this is a 4-bar mechanism. So AB is a link, BC is a link, and then CD is a link, and AD is also a link. So this is link 1, the bottom portion is link 1, this is link 2, this is link 3, and this is link 4. We are going to analyze what are the forces which are acting on this, and not only that, we are also going to find out, we are supposed to find out the input torque T on the link AB for static equilibrium of the mechanism for the given configuration. So on this link AB, what is the torque that is acting? So this is link AB, what is the torque that is acting is what we are going to find out. This is a very simple static force analysis problem. Okay, based on the given data, that is AD, AB, BC and DC, and then D is 35 mm. So based on the given data, draw the sketch, a simple sketch. This is a figure 1. So AB, BC, CD, for this you have to use a compass and a protractor, or if you have a mini drafter, well and fine. And then see this area, that is on link DC at point E, a force of 80 newtons acts. The direction is also given. This is the 150 degree from the ground level from link 1, and so based on this sketch we will draw a simple force polygon. So you have to draw a force polygon, and before that we spoke about what do you mean by a free body diagram. So free body diagram, in the part 1 video we separate each and every link of a mechanism and then analyze how the forces are acting on the particular link. So this is link 3 we have isolated, this is link 4 we have isolated, and this is link 2, that is AB, we isolated. So this is, you call this a free body diagram. So after studying the how the forces are acting, we will be able to understand how well to maintain the equilibrium conditions. Okay, now I will draw this DC exactly parallel using a drafter in this case, and mark this point E, because only at this point E it is given as, that is DE is 35 mm. So from here mark 35 mm, that is from here you can mark 35 mm. Exactly at this point the force F acts. We also know the direction and as well as the magnitude of force F. Now extend this line. So line of action of force F, and mark it as O. So OE represents the line of action of the force F acting on the 4th link. Now draw CO and DO such that, which represents, sorry, so this is initially you have to draw CO parallel to the link 3, CO parallel to link 3. So they meet at this point and extend D to O. So this represents the line of action of force F14. So this represents F34. So when you separate link DC, two forces are acting at D and also at C. So line of action of there is a force F34 is acting here, and here F14 is acting in this part. So in order to determine the line of action of F14, I repeat, draw a line parallel and then mark a point E exactly 35 mm based on the given data. This is the given data, and then extend this line and then draw CO parallel to this, which represents the line of action of F34, and when you close this, you will be able to get the line of action of force F14. Now, based on this, draw a force polygon. So it is given as 80 newtons. Again, you can assume that 2 centimeter is equal to say 25 or 20 newtons. It's up to you. So if you make 2 centimeter is equal to say 20 newtons, so it will be around 8 centimeter. So this will be around 8 centimeter. Now draw AB parallel to this line of action of F, that is line of action of force F, and then F34 you join. So F34 you draw BC parallel to the line of action of F34, and then you extend this, and then F14. Now draw the line of action of F14 here. Draw CA parallel to F14 so that they meet at point C. Hope you are able to understand this step. So I repeat again. You can take it as a suitable scale. It's up to you. You can say 1 centimeter is equal to 10 newtons, or 1 centimeter is equal to 30 newtons. It's up to you. Now draw AB to a suitable scale based on your choice in terms of newtons. So here you can assume 2 centimeter is equal to say 20 newtons, or 1 centimeter is equal to say even 30 newtons or 25 newtons. It's up to you. Now AB, draw AB parallel to this line, and then from here, from this point BC, draw a parallel line to the line of action of F34. Either you can draw parallel to this or to this. Then you extend this, and then you can bring the mini drafter such that at point A, draw parallel to this line such that they meet at point C. So the point where it meets, join BC. Thus we will be able to determine the magnitude of F14 and as well as F34 based on a simple conversion. Okay. Now this is link 3. So as you can see, on link 3, force F23 is acting. F23 is acting, and again on link that is link 3 at point C, F43 will be acting. So this, it will be acting like F43 will be acting. That is what is being displayed here. F43 at point C and F23 at point B. Okay. Now this is link 2. Separate link 2 from the actual space diagram, and then draw F32 parallel to this line, because on link 2 you have two forces, that is F12 will be acting and as well as F32 will be acting here. So here F32 and here it will be F12. That is what is being shown here. See this F32, just draw F32 and draw exactly parallel to F32 from point A. Hope you will be able to understand. So based on this only we will be able to find the direction of the line of action of F12. I repeat again, separate this link from the space diagram and then extend F32, that is extend from here, extend the line F32 and then draw another parallel line parallel to the line of action of F32 which represents F12. So this is the torque as we saw earlier in the previous slides. So similar to this. So for static equilibrium condition it must be F1 into H is equal to F2 into H. So these are static equilibrium conditions. Apply the same formula. Yeah, here also apply the same formula. Now, so F34 is equal to minus F43, which is equal to F23, which is equal to minus F32, and this negative sign indicates that the direction of line of action of F23 and F32 are are different. That is, they're exactly opposite and equal in magnitude. So this minus indicates that F23 is equal to minus F23 in the sense they are both equal in magnitude and as well as opposite in direction. So that is the condition for us. That is F23 is equal to minus F43. F23 is equal to minus F43, and similarly, yeah, F43 will also be opposite to F34. Thus, we found out, and not only that, you have to measure the height. This height between these two parallel lines. So extend this line and extend F12 here, and you can find the height here, or you can also find the height here also. And remember that this height h is not the length of the link. Many students they get confused. Usually they will take the height of this h is equal to the length of L, they assume. It's totally wrong. You are supposed to take the distance between the line of action of F32 and line of action of F12. Thus you will be able to determine the input torque value. But we also know that the input torque has to be equal and opposite to this couple. So T will be a positive value. So though minus F32 into H is equal to 47.8, this is what was found out from here. F32. So this F32 is found out because this F32 will be found based on this. There is F34 minus F43 equal to F23 equal to minus F32. So the moment we find out what is F34 and F14, all these lines, those things which are equal and opposite will have the same magnitude. So this F34 will be equal to F32. F34 is equal to F3 minus F32. So substitute the values and then find the answer. It will be negative, but since the input torque has to be equal and opposite to this couple, T will be my 18.78 Newton meter. That is a positive value, Newton mm. Okay, thus we found out the answer. Now we'll proceed with another example, a slider crank mechanism. These are the given data. Theta is equal to 60 degree, and then determine the forces on various links and the driving torque T2. Similarly to the previous one, in this case it is a 3-bar, it is a slider crank mechanism. It is a slider crank mechanism. So this is a slider, this is the connecting rod, this is the crank, and this is link 1, link 2, link 3 and link 4, and force of 2 kilonewtons is acting. And similarly you have to draw a free, this is drawing the space diagram, you have to draw a free body diagram, that is separating the links. Separate link BC and then you find out F23 is acting. So F23 will be acting here. In this case F43 will be acting on this link. That is what is being showed here, F43. And then separate link 4, that is a slider. On this F14 will be acting exactly perpendicular to this line of stroke, perpendicular here. This is the force F, and this is F34. Now we will draw this. Since it is assumed 1 centimeter is equal to 40 newtons, you can also assume as 1 centimeter equal to 400 newtons. But 1 centimeter, if you assume 40 newtons, it will be we won't be able to draw it on a A3 sheet. It will be very large. So assume that 1 centimeter is equal to 400 newtons. You can assume 1 centimeter is equal to 400 newtons, and draw OA parallel to this line, parallel to the line of action of force F. Now again we know the line of action of F34. So from here draw a line parallel to this link. To this link you have to draw a line that is parallel to that is the line of action of F34, and this closing side we know F14 will be perpendicular to the slider, that is this will be perpendicular. So draw F14, thus the value of F34 may be determined, the value of F14, there is a magnitude of F14 and the F34 may also be found out by converting them into the suitable scale. So this is a very simple example, and so the input torque T2 we are supposed to find. So again separate the link 2. We know the forces will be F32 and as well as F12. So after separating the link, so by drawing using a mini drafter, bring the drafter, draw a line parallel to this link, and then you can mark F32 such that this the line of action of F32 will be parallel to this, and we know F12 will also be parallel to F32. So draw F12 parallel to the line of action of F32, and also find the height between this line of action of F32 and line of action of F12, and thus substitute in the simple formula, that is F32 into H. So it is found out around minus 167.9 Newton meter, and we know the torque value will be positive. That is as in the earlier example, the input torque has to be equal and opposite to this couple. It will be a positive value, and remember the F34 is equal to minus F43 equal to F32 is equal to minus F23 equal to F21, which is equal to minus F12. So based on this link, that is F23 equal to minus F43, we all know F32 is equal to minus F12, and I think it is very easy to comprehend. And thus we have seen two examples of static force analysis problems, and I think as you work out it will be very easy. Not only by looking at this video, I want you to roll up your sleeves and then take out a mini drafter and then try to draw the diagram and find them out. It is a very easy method of finding out the input torque which is acting on a slider crank mechanism in order to move the link AB. So thanks for watching.